Today we are going to talk about the little bit about the midterm 2 preparation, and we'll try to discuss some of the points about the assignment 3. So in midterm 2 preparation, which is already posted on your blackboard. So the goal and topics of this midterm is, the goal is to just help you to systematically review the basic knowledge in computer architecture basically. And only basic knowledge is tested. There is no critical questions that will be given to you, and there is no tricky questions. The topics which are covered in this midterm 2 examination is your basic CPU implementation, and the pipelining, where we talk about the your non-pipe and your pipe part. And then in speculative execution, we mostly talk about the branch prediction, which we discussed in our previous class. So for you, it's through online only on Blackboard, as we did in the midterm 1. And the time is, as usual, your session time from 6 to 7:15. So this time 1 hour 15 minutes given for your midterm examination. And obviously it is a closed book one, and close notes and close everything. So you may use your the calculator, but it is not required basically. And as said, do not waste your time. If you stuck on a problem, just move forward and retrieve the problem later. The exam is a conceptual, having some conceptual questions and some problems. So there will be total 16 questions are there. In this 16 questions, it will cover the 3 topics of your basic CPU implementation, pipelining, and your branch prediction part. It is a short answer question type. For your the pipelining, you need to create a table in the answer. So in that table, you will have the first column. You need to, as we did in the assignment, the instructions will be there, and then you will be having the cycles 1, 2, 3, 4, 5, and it's so on, continue, and then you start writing like the IF ID for any instruction, like instruction 1. Then you need to write ID, your exam, the execution mode, your memory access, and your write back type. And this will continue, and as you did in your assignment, so after doing this exercise, you will find what are the number of cycles are there. So that you need to write. If the number of cycles are suppose 12, then you can write as 12, and then during the grade process, every instruction in which cycle they are finished, that will be checked out for every instructions. There is a question here: is the test auto graded by Blackboard? No, the grader will grade accordingly. And then this exam, mostly the problems will be similar to your assignment 3, but not exact. Similar questions will be there. And don't leave any question, because there is no penalty for any wrong questions. You need to show your work and provide the justifications and mathematical calculations perfectly for this. So the materials to review for this, you just go through the slides which I have provided to you on the blackboard, and some exercises you can go through the optional textbooks. And all questions are mostly from your slides only, but for your additional information and additional practice, you can go through the optional textbook. And make sure to always get the latest slides from your Blackboard. Just recently which was uploaded. I hope everything is updated and you are going through the updated slides only. And then including your assignment 3. So assignment 3 will be graded soon, and before your exam, you just check on the Blackboard whatever your submitted answers are there and whatever the correct answers that you can find on the Blackboard itself. Okay. So there are some questions in the book. What's the best way to make that table on Blackboard? You just create on Blackboard. When you go, you can create the table option is there, and then you can by clicking on that table, you will find some options at the bottom to add columns as well as the rows. Yeah, Blackboard allow you to make the tables. Blackboard allow you to make the tables. Yeah. So, and Blackboard, when you go, there will be one table option will be there in the format that in the table option. When you click on that, first initially it will give 10 by 10 only. So after that, once the table is there in your answer workplace, there if you click on this table, then you will find some kind of icons like some row type options will be there if you click on that. So if you want to add columns, then here one option will be there. If you click on that, then that will add some extra columns, as well as same kind of button will be appear for your row also. If you click on that, then additional rows will be created for you in that. So that you try to practice so that you don't find any difficulties during your assignment. You might have find that one. A bit slow at getting. Okay, so I have been able to copy and paste some tables for some questions, but not always. So, yeah, you can do a lot of practice over there. Yeah, so next, we'll try to move forward. So you can check out the textbooks, but it is not required as said. So there are some differences in the details between my slides and the textbook. But please follow my slides in this case. So then the first type of questions which covers your basic CPU implementation, that know the 5 stages of your risk, and how and know what does each stage do in your instruction fetching, decoding, execution, memory access, and your write back. And particularly the instruction decoding and your memory access each has 2 different operations. So the question we ask you, like let me ask you some questions that what operations does the first phase of your risk implementation? Can you guys write the answer in the chat box? What operations does the first stage perform? Let me write what operations does the first stage performs. Write the answers. It's instruction fetch. If you give this answer, then it will be, you will get 0 points. specifically at what operations does the first stage perform? First stage is obviously instruction fetching stage, but what are the different operations performed in that? PC increment, ALU is wrong. PC plus 4, that's correct. PC counter and PC. Okay. Yeah, PC is one operation, and you will find first. You are going to find, if you recall, that first what is happening, your instruction memory read operation will be performed, and then your program counter will perform program counter. So you must write that instruction memory read operation, and program counter increment, or you can simply write program counter increment like PC plus 4. If you write the answers like this, then that will be accepted. Okay, so let me ask you another question. What operations does the second phase or second stage performs? What operation does the second stage performs? Yeah, Thomas, you're right. Read address of next instruction, read that instruction from instruction memory, and send. That's correct. Yeah, so what about the second stage? What operation does the second stage perform? Read the operation code. Sign extension, get values. Okay. That's fine. Okay, so it performs basically two major operations. One, there is an instruction, correct? So first, it will do the for the second stage, it will do first the instruction. Your instruction decoding will be done. Instruction decoding will be done, and your register is read. Your register file read operation will be done here. Okay, so suppose what operations does your third stage performs? The third stage, what are the different operations it performs? The third stage, ALU operation and zero detection from Benjamin. ALU and zero, Julian. ALU and zero. Performs arithmetic operation. Okay. Remember, you need to cover all the operations which are performed at stage 3 or stage 1, stage 2, stage 3. So it covers the functional unit ALU is there that performs the ALU operation, and zero functional unit is there, another hardware that performs the zero comparison. That's perfect. Okay. So what operations does the fourth stage performs? In the fourth stage, Joseph, correct. Memory access, that's true. That memory read operation will be done. Another one is, another functional unit is there in that. What's that functional unit? We can simply write, memory operation. Okay. Memory load and read is correct. Memory load and store, actually, we say memory read and write operation is acceptable. And another is there, program counter is there in that, right? PC will be updated or not, that decision will be taken. That's good. Okay, so this is one sample kind of thing. The question may be asked like this, or now the question will be asked you like a multiplexer is used to select the inputs, right? We have some multiplexers. Okay, so this multiplexer will takes two input, right? So if you call this multiplexer, how this multiplexers used in the write back stage? How these multiplexers used in write back stage? The questions you just need to write how these multiplexers used in write back stage. So make sure you should describe both the two inputs into a multiplexer. What is the input one? What is this input one? Or you can write the source one and your source two. So what is this source one and what is this source two in the write back stage? What is source one? In the assignment also it is given, right? See, always treat source one is your, the upper input is your source one and the lower input is your source two. Don't confuse. Don't give answer for source one. The upper one is source two and lower is source one. I'll consider the upper input is your source one, lower input is your source two. So in the write back stage, so what is the output? In the write back stage, what are the input? If you go through these slides, the slide you will find there is a last multiplexer. It will get two inputs. There are some answers given. Somebody given that NPC and ALU output. Somebody given source one is ALU output. Memory reader ALU. Could you please expand a little on difference between this and the assignment question? I'm a bit confused. So from the slides, if you find, then that's good. You will find from your source one, you will get the memory, the data memory will be there, or we can simply write the memory is there. Okay. In this, you will find the interstage buffer and memory output given to this interstage buffer, as well as from the previous stage from execution, you will have the what you call the ALU. The ALU output, that ALU output is also given. So your second source will be your ALU output, and first one is, you can find the memory read result. So this is the memory read you will find. So you will get the memory read. So you need to answer in this fashion. So you just need to carefully observe the slide which is given to you for for your risk, what you call the 5-stage CPU, the simple 5-stage CPU in data path, so that you will get that answer. So let me quickly ask you another question. Uh, uh, what are the inputs for your multiplexer 2? Multiplexer 2 in your execution mode. In the execution mode, the execution, you're having two multiplexers. The upper one is your multiplexer 1, and lower one is your multiplexer 2, your MUX. This the upper one, you can write it as your multiplexer 1 or MUX 1, and the second one is your multiplexer 2, and the output of this will be given to your ALU as an input. So what are these? Source 1, your source 2 for multiplexer 1, and for your multiplexer 2, what are the source 1? What is the source 1 and what is the source 2? Can anyone give the answer for multiplexer 1? For multiplexer 1, you're giving the answer of sequence should be clear. The upper one is source 1, lower one is source 2. So for your multiplexer 1, for example, the upper one is coming the input from your the next sequence PC, and the second source for your multiplexer 1 is the output of your register file. Output of your register file. I'll just give you this. This will become your NPC, and this one is your register file output. A register file output, which is there here. So that will be given to this one that we call the register file. Source is register file output. Okay. Yeah. So these are kind of questions that you will get. And just understand these multiplexers. So as I said, the multiplexer is device that selects one of several inputs. And you can also check the clock signal edges, so read and write at different edges, so that first half cycle will be for your write, and second half cycle for your read will be used to solve what you call the data hazard. In the data hazard, read after write cases. So we just focus on this one too for your preparation. NPC and register 1, yeah, NPC and register 1, that's correct. Okay, so that's the kind of question comes from your basic implementation part. And the question maybe ask you regarding the sign extender also. So now comes to the next part, which is covered in CPU components and functionality units used in each stage of execution. So there are questions about these components also, and the multi-cycle CPU design. You just get this benefit of multi-cycle CPU design to answer all these questions. And there are one or two questions will be there regarding the exceptions, so that we have seen that if any exceptions are there, then there will be a hardware part that the exception PC will store the result and pass this after storing the what you call the status of your instruction. It will pass that control to your operating system to handle these exceptions. So that kind of thing you just refer my slides. So second part of your midterm, it will cover your pipelining. In the pipelining, these solutions to all types of hazards, like your structural hazards, okay, as well as in second your data hazards, And third one, you are having the control hazard and their solutions, which we discussed. So this is very important for your examination also. So you just go through lecture sites that has the summary of these solutions, and you also need to know whether the solution can properly solve the hazards or not in particular, and why only the branch prediction is the only the practical solution to control hazards. Why not others solutions are taken into consideration, and does that the data bypassing and forwarding eliminate any stuff or not? Such kind of things will be covered in pipeline. And the question may ask you what is the motivation of employing separate instruction cache and data cache? Any answer for that? Why? What is the motivation? What is the motivation of employing the separated instruction memory and your data memory? What's the answer? Can anyone write down in the chat box? What is the motivation of employing the separated instruction memory and data memory? So there aren't collision between different instructions where one instruction is the memory stage and the other in the instruction stage. Yeah, that's there, but why? Why this memory is separated? Any particular reason for that? By separating this memory, what will be the solution? Oh. So you please go through my lecture slide, then go through my lecture video, you will find the answer for such kind of questions. Is this question solves any of the data, any of the hazards? Is this the answer for this question solves any of the hazards? Perfect. You need to answer like this. Whether it is going to solve the structural hazard or data hazards or what you call the control hazards, that will be the answer, expected answer for this kind of questions. Is my voice is clear? Okay. Somebody is asking which page is that on? You please follow all my pipelining slides, you will get the answer for that. The question is, what is the motivation of employing separated instruction memory and data memory? During the lecture discussion, we have seen that there is L1 cache is used for your instruction memory, and your L1 cache, which is used for your data memory. So one L1 cache separated into two parts. Now this is what we have discussed in the class. You need to answer whether this question will be solving the structural hazard or data hazard or control hazard. So please go through my lecture video as well as the slides, you will get the answer. Okay, and another type of question may ask you that what types of branches can benefit from correlated branch prediction? If I ask the question, suppose what type of branches can benefit from correlated branch prediction, which we discussed in the previous class. You write the answers. Writing loops. If else statements. Actual, okay, if else statement, loops, function calls, switch case, unconditional jumps, error checks. The expected answer for this kind of questions will be, it is simply from the question itself you will get the answer. What type of branches can benefit from correlated branch prediction? That means the branches whose outcomes are related to other branches. Related branches. Yes, Juliet, you are correct. That's good. Okay. So, yeah, these kind of questions will cover in pipelining. And at least one problem about pipelining will be there, which is similar to your assignment 3, to find, how many cycles are there, and you need to draw a table also. In pipelining, I just, said in the first slide we discussed. So then comes to your branch prediction. In the branch prediction, the basic 2-bit saturating counter for the branch prediction will be considered for this mid-2 exam. You need to memorize the state machine. In the state machine, we have find there are 4 states are there: 0, 0 state. Another one is your 0, 1 state. Another one is 1, 1 state. Another one is your 1, 0 state. So upper one we called your taken, and the lower part we consider not taken. So if the state is suppose 0, 0 and your branch prediction, suppose your branch outcome, your actual branch outcome, actual branch outcome is suppose given like taken, 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 not taken, then taken, not taken. Okay. So then, it's actually it starts with the states, okay, with 0, 0. Okay. So this starts with the states 0, 0. Then you need to give the prediction. So here you will find the branches like state. So what you do, we have seen in this 2-bit saturating that if is strongly not taken, and if it is not taken, then it will remain in the same state. If it is taken, then it goes to next state, and if it is not taken, then it will come back to your the same state. And if it is taken, then it goes to next state. If it is strongly taken, then if it is taken, then again it will be in the same state. If it is not taken, then it goes to likely not taken state, likely taken state. And if it is taken, then it will be back to this. And if it is not taken, then it will go to this. So let us see this example in this. Now we need to do the prediction here. Okay, and you need to find out the what you call the states also. So first, what you will do, initially it is 0 0 state. Okay, in the 0 0 state, and it is taken. It is taken. Then from 0 0 state, if it is taken, means it is going to the next state, that is your 0 1. Correct? 0 1. So then you are in 0 1 and branch outcome is taken. So in 0 1, branch outcome is taken. So we will go to the next state, 1 1. Okay. So are you following me? Are you following me? Okay, great. That's good. Okay. So listen carefully. So initially we are at 0 0 stage and branch outcome is taken. So we have taken this from 0 0 state. We goes to let me change the color, blue color. Okay. Yeah. So from 0 0 state, it is branch outcome is actually taken. So from 0 0 state, branch outcome taken. So it reached to 0 1 state. So in 0 1 state, you'll see the branch outcome is taken. So from 0 1 state, you are taken. So you go to your 1 1 state. So 1 1 state is there. In 1 1 state, again the branch outcome is taken. Branch outcome is taken. So from 1 1 state, branch outcome is taken. So it will remain in the same state. So we'll get 1 1. Okay. So then in the 1 1 state, the branch outcome is again taken. So it will remain in the same state, 1 1. Okay. So here also it is taken, in 1 1 state, again the actual branch outcome is taken. So it will remain in the same state. So that is 1 1. Okay. So then in the 1 1 state, it is not taken. So not taken, then it will reach to your likely taken state, that is 1 0. Your 1 0. Correct? So from 1 0 state, it is taken again. It is taken. So from 1 0 state, it goes to the strongly taken 1 1. So in the 1 1 state, the branch outcome is not taken. So from 1 1 state, this is not taken. So it will reach to which state? It is 1 0 state. Correct? Likely not taken part. Okay. So first you have done these states. Are you following me? How these states are generated? Very good, super. Okay. So next what we do, we need to find the hardware prediction. We need to find the hardware prediction. So we need to find this prediction, right? So in prediction, 2-bit saturating, what happens? It always starts with 2 not takens, right? That we have seen in the example, 2 not taken. So first it assumes not taken, but actually it is taken. So there is one conflict, but still it will not change its decision. Okay, it will again go with the not taken. But in this case also it is taken. So there are consecutive wrong prediction is there. Then the hardware change its decision from not taken to your taken, because previous history is used for prediction. Okay. Now the hardware predicted taken and actual outcome is also taken, so it is correct. So it assumes from this previous history, okay, it can predict that it will be taken. It will be taken. And the branch outcome is also, actual outcome is also taken. So both are matching, right? So then it, from this history, it will predict taken, taken. Again, here is taken and branch outcome is also taken. So both are correct. So in the future, it predicts the branch will be taken. Branch will be taken. Correct? Now, here branch hardware branch prediction is taken, but actual branch outcome is not taken. So only one here is first wrong or only wrong prediction is there. So it will not change its decision from taken to not taken. It will still predict in the future as taken only, taken only. So here branch outcome is true. So here again it is matching. So it will not change its prediction now, taken only. Now from this history in the future, it is taken and it is also taken and assumes in the future also it will take. It will take. But the branch outcome is not taken. Branch outcome is not taken. So the wrong prediction is there. Only one wrong prediction is there. Okay. Actually, if there are consecutive wrong prediction, then only it will change to its decision from taken to not taken or taken. Okay. So now from this history, in future it predicts that it will be taken. It will be taken, and whatever is there, that will be compared now. So this process will be continued. This process will be continued in 2-bit saturating. Is that clear now? Is this clear? Okay, that's good. So you will get this kind of question. You will get this kind of question in our what you call the exam. Okay, so here just the implementation of your branch prediction buffer and branch target buffers. So what components does this two buffers have, and how does a branch locates its entries in the two different buffer part? That is how we just maintain how you are going to maintain the states. Okay, and the correlating branch predictions, that why does correlating branch predictions works for some branches, and why does correlating branch prediction not work for some branches, and like whatever we have seen right now, the 2-bit, so you will get the global branch history table part. And there will be one problem about branch prediction, as we just discussed, which is similar to the last question of your assignment, as well as whatever we discussed right now. So this will be what you call the given, and let me just ask you some questions for exercise. Let me just share this the screen with you, which we have done this exercise in our class also. Yeah, we have just introduced the buffer part. We haven't gone through, so there is no science to be expected. That's it. But we have seen that for 2-bit saturating counters, how many states will be there? For 2-bit saturating counters, how many states are generated? Correct. Likewise, if there are, suppose, 3-bit saturating counter is there, then how many states? If there are 3-bit saturating counter, then how many states? Very good. For 4 bits? For 4 bits? Wonderful. Good. Likewise, for 5 bits? Very good. Okay. Yeah, that's correct. 32. 32 states will be there. Okay. So now I think the screen is visible to you guys, right? Very good. Super. So now let us do this exercise together once again, which we already discussed in our previous lecture. But let us, yeah, Julian, that's correct. So let us discuss this. Now we have the hardware component which maintains these states. This hardware component which is maintaining these states. Okay. So again, let me just give you at 0 0 state. If the input is not taken, if input is not taken, it will remain in this. If the input is taken, if the input is taken, it goes to your next state, that is 0 1. And if it is again not taken, then it will go back to it's strongly not taken. And if it is taken, suppose from this stage, then it goes to your strongly taken state. Okay, if it is taken, and then if it is again taken, for example, then it will remain in the same state. If it is not taken, then it goes to your likely taken state. If it is not taken, goes to likely taken stage. If it is taken, then it will come back to your strongly taken stage. And if it is not taken, then it goes to your the strongly not taken state. Okay. So now tell me, what is the entry here? What is the entry here? Can please write your answer in the chat box. What is the entry for second row of state column? 0 1 0 1 0 1 0 1 0 1 0 1. Very good. Yeah, I appreciate it. So we actually we are at 0 0 state, and it is taken. It is taken. So it will goes to next state 0 1. Answer is correct. Okay. Now we are in state 0 1, and actual branch outcome is taken. Okay. So what is the entry? What is the entry? Let us see this: first row, second row, third row, fourth row, fifth, sixth, seven, and eight, suppose. Okay. So what is the entry at the third row state column? What is the entry? Wonderful. Okay. Good. So it is 1 0 0 1 taken. So 0 1 taken, it is going to your 1 1 state. Okay. 1 1 state. Wonderful. At 1 1 state, again it is taken. What is the answer? Good. Okay. So from 1 1 state, it is taken, so it will be remain in the same state 1 1. Good. So next, in 1 1 state, it is taken, branch outcome is taken. Then what's the next state? What's the next state? Not 11, it is 1 1. Okay, great. So it is remain in the same state. Wonderful. Okay. So now at 1 1 state, again it is taken. So it remain in the same state. Okay. Okay. At 1 1 state, it is taken. So again it is remain in the same state. Good. And okay. Now at this stage, what's the answer? It is 1 1 state and not taken. 1 1 state not taken. Answer is 1 0 1. So it is likely taken. So it will goes to after this, it will goes to your 1 0 state. Wonderful. Okay. At this not taken. After that, suppose if it is taken, then what is the ninth entry? Expected ninth entry? Your ninth row entry? Let me write column 1 or column 2 or column 3. So what's the entry of your ninth row? 1 1. Strongly taken. Super. Okay. So it will be 1 1. Great. Okay, so now let us do this prediction. Okay, let us do this prediction. So what will be the first entry in the prediction column, first row? The answer is not taken, not taken, not taken. Okay, there are so many not taken answers are there in chat box. Okay, so let me fill this with not taken. Let me just change the color. Okay, so most are saying that it is not taken, and the answer is not taken because it starts with this. So what is the next entry here? Next entry, second row, second column. Wonderful, wonderful. Okay, so it is also not taken. Super. Okay. But in these two cases, actually it is taken. So the prediction is wrong. So what is the entry at the third from this history? What it will do? Great. Okay. So it is changing to your tree because the consecutive two wrong prediction. Wrong prediction. So it will change its decision from not taken to taken. Okay. Now, up to here, it is taken. And in the future, what it will do, it is taken and the actual branch can also taken. Okay. So in the future, what will be the entry? What is the prediction of this hardware? Good. Okay. Most of the answer taken. So let me give the correct answer is taken. Okay. Now, this current prediction is taken and current branch actual outcome is also taken. So they are correct predictions. So what it will predict? It will predict to taken. Correct? And the actual none is also taken. That's good. So then it will predict in the future as taken only. And here also it is taken. So that's correct prediction of your hardware. So in future, it will predict again as taken only, but the branch actual outcome is not taken. Correct. So what will be the output from these two, taken and not taken, of your 2-bit saturating? What is the entry for 8th row, second column now? Likely taken. Correct. So it is likely taken. So it predicts that it will be taken. It will be taken because only one wrong prediction here. Okay. So then it predicts that taken and the expected actual branch outcome is also taken. Then what the entry in the 9th row now? Wonderful. Yep. So it will be taken. Okay. So I hope now it's very clear for you, right? So this is the expected, the what you call the answer from every student. Okay. I think this kind of questions may get around 10 to 20 points. If you do this exercise, then it will be helpful for you. Okay. And if you recall this, we have seen this exercise in this branch prediction. If you see, we have seen these examples. There is one branch. That branch is taken this. The branch outcomes are like taken, and we have seen this example. If there are consecutive not taken and the actual branch outcome is taken, then only it will change its decision. It will change its decision from not taken to taken. But for single wrongs, it is not changing, not changing, not changing. Okay, so you can expect this kind of question. Okay. Yeah. So then, suppose here the question is: suppose if it is a 3-bit saturating counters. 3-bit saturating counters. Okay, so then what are the initialization of this 2-bit saturating counter for hardware prediction? For 2-bit counter, it is 2 consecutive not taken, right? It starts with 2 consecutive not taken. If it is 3-bit saturating counter, then in 3-bit saturating counter, yeah, guess, give the answer. I expect answer from the guessing answer from every student. Wonderful. Yeah. Yeah. That's good. That's good. That's good. Okay. That's correct. It is 3 consecutive notes will be there. Suppose if it is a 4-bit, then there will be, after 4 consecutive wrong decisions, then it will change its status from not taken to taken. So we call this like this. It may be 3-bit, 4-bit, sorry, 2-bit, 3-bit. We have seen 1-bit also, 5-bit, and so and so up to n-bit. No, you can do the same exercise. We call that as your global history table. Okay? Yeah, global, the buffer history table, which we have maintained here in our example. Then we call that your global branch history table. That hardware will maintain this. So we have seen the history of this one. Okay. So this kind of questions will be expected from this point of view. I hope it is very clear. This branch prediction buffer is very clear. Okay. So then, you will get the some questions from pipelining. You will find like similar type of questions from your assignment. For somebody saying that we haven't got, yeah, we have gone through this slide, but we haven't discussed, more about this one. So the question may be, a similar type of question which I just asked you. That kind of question will be asked in the exam. That is for 1 or 2 points. The question which I just asked you, right? In 2-bit saturating, 3-bit saturating, and 4-bit saturating, how many consecutive nodes will be there? That kind of thing. Or if it is 3-bit, then how many states? Which I just asked you. If it is a 3-bit, sorry, 2-bit buffer, then how many states it generated? As we asked. If it is 2-bit, then we wrote that to the power of 2, 4 states. If it is suppose 3-bit saturating counter, branch prediction buffer, then we write to the power of 3 is equal to 8 states, and so and so. Yeah. So yeah, so these are a few things that will be covered, and yeah, that's all from my side today. Hope you got the clear-cut idea about what kind of questions are expected in the mid and how you're going to answer those questions. Okay, so with this